Hello chemists, this is Ms. Placino and you're watching lesson 10.2 on solubility. Today we're going to talk about the different factors that affect the solubility of a solute. Lots to do today. First we're going to discuss the differences between saturated, unsaturated, and supersaturated solutions, so some terminology to tackle. We're going to use table F for predicting the solubility of an ionic compound in water, and we're also going to use table G to predict whether a solution is saturated, unsaturated, or supersaturated. So you definitely want to have your reference tables handy for today. And finally, we'll talk a little bit about how environmental conditions impact solubility. I'm here to say that really is the big one for today. Being able to use table G, a new table, is going to be really important. Let's get started. So first, let's talk about ionic compound solubility. We know that ionic compounds will dissolve in water if they are soluble. And to predict solubility, we've got table F. We've seen this table before. We used it back in Unit 5 when we're trying to predict whether the products of a double replacement reaction would be soluble or insoluble. So just to kind of quickly review how to use the table, over here, on the left side, we've got ions that form soluble compounds, or ions that tend to form compounds that dissolve in water. You can read. Exceptions tend to be insoluble. So when I take something like silver, for example, and I combine it with bromide ions, even though bromide is typically going to be found in compounds that are water soluble, silver bromide is an exception and will form an insoluble compound, so that will not dissolve in water. If we take a look at the right side of the table, we tend to look at anions that are going to form insoluble compounds. So for example, carbonates tend not to dissolve in water. Our exceptions on this case side are, I call them slightly soluble. So if I take a group 1 ion and combine it with carbonate, for example, sodium carbonate, and I try to dissolve that in water, it will dissolve. So just hopefully remember how to use this table. Let's do a couple of practice problems to make sure we've got the hang of it. All right, so using table F, I'd like you to take a look at, that's a big one, A through D. Go ahead, use table F and predict whether those compounds will be soluble, insoluble, or slightly soluble, and we'll review when you're ready. All right, let's check these out. Calcium chloride. Chlorides are soluble. Calcium is not an exception, so this should be a soluble compound. Ammonium sulfide. Sulfides tend to be insoluble unless they're combined with group 1 metals or ammonium, which this is, so this would be a slightly soluble. Lithium sulfate. Sulfates are soluble. Group 1 ions are soluble. This will be soluble. And potassium hydroxides. Hydroxides tend to be insoluble unless they're combined with a group 1 metal or ammonium, a couple other cations that also fall in the exception category. Potassium is a group 1 metal, so it should be slightly soluble in water. Right. Feel free to practice with the other ones to make sure you've got the hang of this concept. Let's head back to the notes. So assuming that our solute is actually soluble in the solvent, we can have solutions that take on 3 different states, is what I call them. They can be unsaturated, saturated, or supersaturated. So let's just kind of define what those terms mean. When we talk about an unsaturated solution, really we're just saying the solvent is able to hold more solute. So you take just a little bit of sugar, you dissolve it in some water, there's still room in the solvent to dissolve more solute. So the solid would dissolve when it's added to the solvent, and you'd be able to keep that homogeneous mixture. So when you think unsaturated, just think able to hold more solute. If you continue to gradually add solute, eventually you'll reach something called the saturation point. You'll form a saturated solution. When the solution is saturated, it is full. It cannot hold any more solute. This technically exists at equilibrium, so we've got 2 opposing processes occurring at the same rate. So if we think about a saltwater solution, let's say, and we know that it's saturated because we've kind of piled up a bunch of stuff at the bottom. There's just extra solute sitting there. This solution itself is saturated, so it cannot hold more solute. So as I add more solute in, it just kind of collects at the bottom of the, in this case, beaker. When you say it's at equilibrium, that pile of sodium chloride that's building up at the bottom, sometimes we'll see some of those sodium and chloride ions dissociate and join the solution. But in order for that to happen, sodium and chloride ion have to kind of come back together to reform the solute, and we'll end up reproducing more of this solid. So that's the equilibrium we're talking about, the dissolving kind of in this equilibrium system or this reversible system with crystallization. I apologize for my writing there. That is pretty rough. There are times when you can kind of like almost trick the solution or the solvent into holding more solute than it should be able to under a given set of conditions. When that occurs, we say that a supersaturated solution has formed. This is an example of a supersaturated solution that has been disturbed and now materials have come out of solution. So basically, the solvent is holding more solute than it should be able to. So we should have a saturated solution with kind of a pile of solute sitting at the bottom of that vessel, but we've been able to coax the solution or the solvent into holding more solute. If I add just a little bit more solute, or I kind of disrupt that system, like if it's in a beaker, I kind of just tap it hard against the bench or the desktop, I can sometimes disrupt it enough to cause everything to crash out of solution. And I want to show you what I mean. I've got a quick video about a supersaturated solution. In this video, we're going to be looking at supersaturated sodium acetate. And sodium acetate is one of the substances that is able to form a supersaturated solution fairly easily. All right, so we've got our supersaturated solution, and if you take a look at it, it is completely homogeneous. Even though we're holding more solute than we should be able to, it is clear and it looks like any other solution. We're going to take a very small amount of extra solute. So we're taking one crystal. We're doing it very painstakingly. And we're going to add it to our solution. As that happens, adding that single little crystal of solute is causing mass precipitation or mass crystallization. This is not forming a solid, just all of that extra solute that should not have been able to be held by the solvent is now coming out of solution. We'll watch it again in slow motion. It's actually a really cool process to see in person, and as it is crystallizing out, it is also producing a ton of heat. This is a very exothermic process. If you have like reusable hand warmers, often they use sodium acetate as the reactant in those. So to kind of help you visualize saturated, unsaturated, and supersaturated, I want you to think of our classroom. We've got 36 chairs in our classroom. So we'll have the chairs kind of represent available like solvent, and students will represent our solute. If I only have 10 students present in that classroom, would you say the classroom is unsaturated, saturated, or supersaturated? Hopefully you're thinking unsaturated. 36 chairs, 10 students, I've got plenty of room to hold more students. So I can keep adding more students into class. How many students do I need to hit like that saturation point? Well, everybody has a chair. At 36 students, that means that I will have a saturated classroom. That is as many students as the classroom can hold. Supersaturated is like if I invite another class to come in. So I've got my 36 students seated. I invite another 34 to come in and to grab a seat. There's no real place for them to sit, per se. So let's say that they're all just sitting on the tables where you're not really supposed to be sitting. Let's say their teacher realizes, hey, my classroom is empty. What's going on? And they come across the hall and they open the door to our classroom and come in. At that point in time, because one more particle of solute has been added, all of the students who shouldn't be there because they don't have a chair are going to have to get up and leave. That's a supersaturated solution where we somehow have, in this case, more students sitting than we should be able to because we don't have enough chairs, and we disrupt that solution, and those extra solute particles are going to come out of solution. Hopefully that helps you visualize it a little bit. All right, before we get into using table G, I want to talk about factors that affect solubility. You know from experience that changing things like, in particular, temperature will impact the solubility of different materials. Think about trying to dissolve sugar into hot coffee versus iced coffee. It's not the same. So if we look at different factors affecting solubility for solids, high temperatures tend to increase solubility. You should be able to dissolve a whole lot more solid in a solvent that's at a high temperature than at a low temperature. You just have more effective collisions. If you try to change the pressure, it's going to have virtually no effect. So this isn't something that we can usually change very readily. But even if we were, we can't force more solid to dissolve simply by changing the pressure. For gases, something like soda or champagne, where we've dissolved a whole bunch of carbon dioxide into a mostly water solution. Low temperatures actually increase solubility. Why do you think that is? At high temperatures, what's going to be true about the amount of movement of your gas particles? Higher temperature means they're going to be moving more quickly, and they're going to be more likely to escape. If you've ever left out like a glass of soda or something, you know that over time, once that kind of reaches room temperature, the soda tends to go flat. That doesn't happen as readily if that same glass of soda is refrigerated. Gases are very sensitive to changes in pressure. So if we have high pressure, we can force more gas into the solution, ultimately increasing solubility. Something like champagne, it's not uncommon to have that bottled at about 8 atmospheres of pressure. So you can try to force in as much carbon dioxide as possible. And we'll really be able to see the impact of temperature in particular on the solubility of solids and gases as we get into table G. All right, so let's talk about solubility curves. And I want to start with just this very simplified curve. Table G has over a dozen different curves on it, so I want to focus on just one at a time. Here we're looking at potassium nitrate. Along the x-axis, we have temperature, degrees Celsius, and the y-axis, we have grams of solute per 100 grams of water. So basically, you think about a beaker with 100 grams of water in it, and I'm going to start adding just potassium nitrate and see when the solution becomes saturated. If I'm anywhere below the curve, I am unsaturated. Again, unsaturated means the solvent is holding less solute than it can under the given set of conditions. So let's say I've dissolved 100 grams in a solution, 100 grams of potassium nitrate in 100 grams of water at 80 degrees Celsius. Well, it's below the curve, so this would be an unsaturated solution. I could still add more potassium nitrate to that 100 grams of water before it is full, if you will, of solute. Once I reach the curve, you're looking at a saturated solution. There's only one mass of solute per temperature that corresponds to being saturated. Just like in our classroom example, only one number, 36 students because of 36 seats, is going to correspond to the classroom being saturated. So if I'm at 80 degrees Celsius, if I wanted to saturate the solution, it looks like I'd probably be at about 160 or so grams of potassium nitrate. If you are above the curve, most students want to say, oh, it has to be supersaturated. Be careful. It really depends on whether the solute is visible or not. If you cannot see any solute, so if there isn't any of it collecting at the bottom of the beaker, the Erlenmeyer flask, or whatever you're making the solution in, then you have a supersaturated solution. So no visible solute. If you do have that little pile of solute sitting at the bottom of the beaker, you have a saturated solution. The excess solute has not dissolved. So again, kind of what that would look like. I've got my solution. I've got some of the undissolved solute. So the solution itself is saturated. And then I just have excess solute sitting at the bottom of the beaker. This is the more common situation. It's not very often that we get things to supersaturate. Some materials just aren't able to supersaturate in water the way something like sodium acetate can. Let's try some practice problems. All right, so I just want to try out a couple of these and look at the different types of problems that we can answer about solubility curves. I think one of the hardest aspects of this graph is just making sure that you are looking at the correct curve. There's a lot going on in there, especially like kind of in this section. So it's really easy to literally get your lines crisscrossed, so be careful. All right, question number 2. How much KNO3 is needed to saturate 100 grams of water at 60 degrees Celsius? Okay, well, I'm always working with 100 grams of water, according to the chart. So I'm going to find 60 degrees Celsius, and I'm going to trace up until I find the KNO3 curve, which is up here. So, at about that point is where I hit the line. Trace across, somewhere between 100 and 110. Looks like it's pretty close to the middle, so I would call this 105 grams of KNO3. If you see it as like 104 or 106 grams, that is plenty close enough. These often show up as multiple choice questions, and they're not just separated by 1 single gram. Let's check out another one. At what temperature will a solution containing 60 grams of ammonium chloride become saturated? Okay, so we're kind of going in the opposite direction now. I've got 60 grams. I'm going to go across until I find my my ammonium chloride. It's kind of about there. Trace down. Maybe 66, 67 degrees Celsius. Pause the video. Try out questions 4, 5, and 6. And then we'll regroup and review them together. So question 4 is a little bit more complicated. How much KCl would you need to add to 100 grams of water already containing 30 grams of KCl to saturate the solution at 80 degrees Celsius? All right, so first let's figure out how much KCl would be needed to saturate this solution under the given temperature conditions. So I've got my 80 degrees Celsius. I'll trace up till I hit KCl. And it looks like it's just a hair over 50, so we'll call it 51 grams are needed to saturate. I already have 30 grams present in that solution. Do some really high level math here. Yeah, I need about 21 grams of my KCl to saturate this solution. All right, question 5 is asking us about the state of a solution. So unsaturated, saturated, supersaturated. We've got 50 grams of KClO3 at 80 degrees Celsius. All right, back at 80, KClO3, that's this curve right here. So it looks like maybe 45 grams or so are able to dissolve. We've dissolved 50 and there's no visible solute. Hopefully you're thinking this is a supersaturated solution. If solute was visible, that would mean that the solution was saturated because it couldn't hold any more. But since we are over the line and no solute is visible, that describes a supersaturated solution. All right, last of the 3. We've got ammonia solution at 60 degrees, 50 grams of water. All right, so 60. Let's find the ammonia curve. Ooh, there it is. Yeah, maybe that's about 22 grams. Careful. It says that we're working with 50 grams of water. If you look at the label on the y-axis, this is solubility per 100 grams of water. If we're cutting the volume of the solvent in half, what do you think we need to do with the mass of the solute? Yeah, it's also going to be cut in half. So if you have half as much water, it will be able to hold half as much ammonia under the same conditions. So that one is 22 grams. 22 divided by 2 gives me 11 grams. All right. Nice job with this, chemists. I would suggest keep on practicing. Just get familiar with using this table and really comfortable and confident with it. And that wraps it up for today. All right, thank you for tuning in, and I hope you found this helpful.